So yeah, we were just talking on the break about how complex the inputs to the NMR are, and we're gonna be changing some things to try to do this matching. But you know, it's definitely a non-unique problem, and there's a million ways that you can change your results, and also they may never match because of sometimes the service company does some really specialized inversions and uses very specialized sequences. But I think the ability to have so much flexibility in the input does give you a chance to build up some intuition on how different things are going to affect the NMR distributions. And so you'll see in here that you can try so many different things, and they can have big effects on the distribution that you finally see. So what we're going to do now is start making some changes to the Earth model to try to get this to look more like the initial or the imported distribution. So one of the things that we notice right off is that our shale peak is way off down here, where we have this high shale volume. We see that if you put your cursor over it, you can see that the peak here is centered around T2. Looks like 1.4 milliseconds or so. Well, maybe even less, 1.1 or something milliseconds. And then up here, we're closer to like 7 milliseconds. So what we can do is, you might suspect that since that seems to be the same everywhere, that might be due to the pore size distribution. So we'll go here and we'll open up the NMR rock class, and we're going to look at the shale distribution, and you can close other ones that you're not interested in. So for instance, if we're not going to change the shape function, you can close that. And again, this is one of the most, this is one of the areas where it gets really complicated, because you have all these different pore dependent properties, and they all have a big effect really on the results. I mean, the water saturation, pore dependence, or the surface contact pore dependence, all have a big effect. But the main thing that we're going to do right now is look, you have two pore radius distributions. One is for shale. We have a separate one because we consider in UTEP wells, we usually have, as you saw in the palette, we have two separate solid components. You have the shale and the matrix, and so they'll have different components, and they'll have different surface relaxivities, and we also generally assume that they're going to have different pore size distributions, and so that's why we made these two here, so you can set your shale pore size distribution independently of your matrix pore size distribution. And so since the shale one was pretty far off, we're going to reduce it by about 1/5. So we're going to go down from, and there's the different ways you can move this. You can either go to the table and set it directly. So you could set the center to 0.02 directly, and or you can change the size using the mouse. And so in this case, we're going to set the width to be 0.05, make it a little bit skinnier, and move it down to 0.02. Okay, so and then we also noted that our oil peak was quite high in here, and so we want to move this down significantly. So what we're going to do is we're going to, because this is bulk oil, we have a limited number of things that we can do with it, because the bulk, in principle, the bulk relaxivity doesn't really interact with much. And so what we'll do is, instead of going to the Brot class, we'll go to the component editor, and we're going to reduce the T2 relaxivity here. So we're going to change the T2 bulk for our oil down to 800. And note that you can give all of these different values if you want. And also you have the ability to set different phases, and we're going to see the effect of that when we do invasion. To say maybe you could try moving the water peak, but basically that would be the pore size distribution in the matrix. But I think we will leave that for the time being and just see what this first step does. Okay, so we're going to those changes. We'll recalculate this. And then we'll go to the simulator. And this time, another thing that will affect the width is the noise. So if you have more noise, you'll usually get a bigger width. So this should increase the size of our, basically all our peaks a little bit. And we can simulate that. Oops, no, that's right, overwrite. And then we will convert this. And now, so now we have more noise. It'll be interesting to see what we get for a regularization. If we check the inversion analysis, so now you see, oh, actually it's 0.5, so it's still using a fairly small one. But now you see that up near the top, like in the short times, they're not matching so well. So somehow our inversions are not coming out quite as perfect as they were before, probably because our shales are slipping off into the short time end of the sequence. Okay, but now we can plot this again. And something looks a little bit funny about that. Sometimes I have to plot something else and come back to it. No, it still looks funny. I think I must have done something wrong again. So let me just double check what I did here. Okay, went to the calculations. Oh, what happened to my, no, shale. Class 0.02, 0.05. Oh, no, 0.2, 0.02, 0.05. That's correct. And this one's the same. Got this set correctly. And by the way, notice on the sequences, there's an outputs that tells you for different sequences what kinds of data it's going to output. So that'll help you to select the right kind of data when you plot it. And then let me check the component editor again. T2 bulk. Exit mean. Looks okay. All right, let me see. Try calculating it again. Maybe I forgot to calculate it. 2. Okay, I'm just trying this again because that was a very strange looking distribution. Oh, I bet you I know what it might have been. Okay, simulation, L3, snack 1. Actually, I'm going to try a custom regularization where I'm going to do 2. Try inverting this. And then let's look at what we get here. Okay, that looks more like what I was expecting. Okay, so all right, so now we can look and we see that we've moved the these oil peaks over a little bit. They're still kind of uniform, but they're closer to where we expect them, and we see that they still trail off, but not quite as badly as they did before. So now they look a little bit more like these, where they just, the tips of them are trailing off. They could possibly be a little bit wider, but we also see that we got these shale peaks down here to be a little bit closer to what we expect, around 1.2 or so, which is about what we have over here. So we can see the effect that changing the relaxivity and the pore size distribution can have. And then up here we have kind of a lot of more fluctuation than I expected, but what else do we say to do? So yeah, we can, one thing that you can do is I did a different, like I manually set the relaxation parameter. And it's funny because, I mean, this has just to do with the calculation of the inversion, but it has a big effect on what you actually see. So if sometimes this thing will automatically select something like 5. And so you can see the effect that you'll have if you invert this with the setting at 5. So now you see that it makes it much wider, probably too wide for what we have here. But I mean, it has a similar effect to increasing the pore size distribution, but it's just an inversion parameter. Similarly, if you have it really small, I think that this is what happened initially, is that the when we let it find its own inversion parameter, it picked something that was very small. And so then usually you'll end up with these very tiny peaks. So if we invert for 0.05, you can see that then this is not very realistic either. And actually, I'm curious what the analysis will show. I mean, the analysis doesn't really look that bad except for at the low values. It seems to be pretty far off in some of these. I'm going to go back to, basically you can adjust this until you get something that you like, which I thought 2 wasn't too bad. All right, so now we can also showed you how to before to calculate the T2 mean with the data set, but you can do the same thing with the imported set. So in this case, we'll change the name to, or not imported, the simulated set. So we'll change this to T2 sim. So we'll get a new log set. And we haven't really tried stacking, but keep in mind that if we want to, we can actually choose multiple stacks here and maybe see which one we like better, unless you know what the stacking of your imported data was. But also the thing is that the stacking here is going to be a little bit different because our sim, well, it's going to depend how you pick the layers, basically. But here we can create this new log set. And then if we go in here, simulated log. Okay, so now we have the sim mean. And let's plot it in the same way that we plotted the other one. Seems darker somehow. All right. So anyway, it's a little bit closer, but not quite perfect. One thing that we see is that the oil peaks are quite uniform here, and they kind of move around more here. And so one thing that we can do is to, we haven't considered invasion. And so one way to get another oil phase that can give us some more complex T2 structure is to do some oil-based mud invasion. And that should put something up here. So what we're going to do is we're going to use the component editor to make a new component, which is going to be an OBM with a custom T2 bulk that we want to be a smaller one, so that it'll move some of these peaks over and mix them up a little bit. So we're going to go into the multi-well. We'll go into the fluid components database. And going to model a new component. We're going to model it off of C22H46. And we'll add a new component. So then we see that we have this copy here. And show the NMR properties here. And now, first of all, we want to change the name. So we're going to call this our OBM. Oops. Didn't want to do that. Okay. So we're going to call this OBM. Oops. OBM. And then we're going to change the T2 bulk to something smaller than we had for our formation oil. So we'll make it 100. And then And then we also want to give it a separate phase, so we don't want it to mix with the other oil because we want to have some more structure to it. And so we'll call that OBM. And so this NMR phase, the way that the NMR calculation works is it divides everything up into different phases. And basically, you always have sort of a water and then hydrocarbon phase. And the hydrocarbon or other fluid phase, you can make as many phases as you want, and they'll all get calculated separately. And so in our basic oil phase, if we go back, well, we don't have it in there yet, but we see that our formation oil has two components. So those will actually get blended together and give you sort of an average T2 based on the sort of a weighted mean of the T2. But it'll be a single peak as opposed to like two peaks. However, if you have more than one phase, so if we add the OBM, that can give you actually two separate peaks because they'll be calculated independently, the same way that the water peak will be calculated separately. And so there's a lot of other things that you can do with the phase. If you go to the rock class, you can set some of the phases as being bulk only. And so that's if, and I've heard of some cases like this where they say that a certain phase is not interacting at all. Basically, it stays in the center of the pore space or in this large pore space centers. And so you can create, you can assign one of your phases as being bulk only, so it will not interact with any of the pore surface or the surface relaxivities. And then oh, I just realized that yeah, I didn't show you, but it's probably easier this way anyway. Originally, I had this set up where you'd create a new rock class, and that was the one that we changed with a different shale. But in this case, we're only going to use, and you can actually get more elaborate effects. I mean, so for instance, if you, in this case, it looks like probably the same shale at the top and the bottom, but I've done some other ones where this one looks different. So then you may want to make another rock class with a different pore size distribution for the upper shale versus the lower shale or something. In this case, we just kept the same one, and it saves us from having to go in and change the rock class in all of the layers, which in the current version is a little bit tedious if you have a lot of layers. But actually, yeah, because you can see that in here, that you can set the rock class in all your layers here, but we don't want to do that for all those layers, so we just change the default since we'll just be using the one rock class. Okay, so and we want to make a new composition. Oh, we want to, okay, we also want to update the compositions. So in the composition database, we can make a new composition. So you see we have OBM1, which is the normal C22H46. But what we can do is we can make OBM2 where we instead select the OBM, and we'll make this OBM2, and then we can Oh, and then we got to set the fraction because we only have one component, and so the fraction is 1. And then we can save that. And so now we'll have another composition available when we want to select our invasion fluid. There we have OBM1 and OBM2. So we're going to use the OBM2. All right, so the next step is we're going to invade. And so for this, we're going to look at the fluid flow simulation. So fluid flow is, in practice, I mean, you don't have to do too much to run it. You have to decide if you want to run it 1D or 2D. So the 1D will not take into account gravity or any transfer of fluids across fluid boundaries. And then the 2D, and actually 1D is often a little bit faster. But 2D, you can take into account gravity if you want to, and it will also, if you have fluids transferring across vertically, then it will take that into account. And then you have the choice of simulating invasion or not simulating invasion, and doing formation test or not doing formation test. Obviously, for right now, we're not going to do formation test. But then if you're going to simulate invasion, you need to set an overbalance pressure. So in this case, we're going to use 300. You need to set a position. This should be somewhere. It doesn't matter so much exactly where it is, but it should be somewhere within the modeling interval. Usually, by default, it comes out at the bottom of the modeling interval, which is the case here. And if you choose water-based mud, you can select your salt concentration, but in this case, we're going to use oil-based mud, and we want to check the new composition that we just made. And we're not going to do it for very long, just 0.025. Or actually, yeah, I forgot, you do it on your own and make 0.025, but actually running it for 0.05 because I want to show you another thing that you can do with the times, the import times. And so this is setting up basically your borehole invasion properties. Then you also have to deal with the simulation grid, which is sort of unfortunate, but so the number of grid blocks, in this case, since we're, so the radial grid, by default, it's 30. Since we're going to be working with NMR, we're really interested in having some reasonable resolution near the borehole. So I'm going to change this to 50. And then the vertical grid, so typically we'll have it, for just invasion, you'll have it evenly distributed because everything's going horizontally. And you don't really care. If you're doing formation tests, then you'll want to do geometrically expanding where it gets tighter around the tool. But in this case, we'll leave it as evenly distributed. We don't need any extra. As you can see on the right, it shows you where all the boundaries are for the simulation grid. That's shown in the red. In this case, we have more than 30 layers. And since we said a minimum of 30 grids, we have basically one grid per layer. But if we had more, you could change the number of grids. And there is no azimuthal issue with invasion. It just invades azimuthally uniform. And so the dark and the light here just show, it's just a way of easily seeing where the different petrophysical layers are. If you had more fluid layers, I guess we can actually show what that would do. If we put 60 here. You can see initially we had, so now you can see the grid, because we said minimum number of 60. We wanted a finer grid for an example. You can now see that some of the thicker petrophysical layers are going to have multiple fluid layers inside them. And that can be important in some different cases if you're doing, if you have a preset fluid variation, or if you're using a water oil contact or something like that, where you're going to have a fine fluid variation that you want to take into account the fluid variation across a particular petrophysical layer. And down here, you see the actual number of grids. We set it to 60, so it made 60. The reason we have this is because there are constraints on where it can put the grids, and so you won't always get the exact number that you say up here for your minimum. It could give you more if it needs to. For instance, if we set this to 20, we still get 47 because it has to at least have one grid per petrophysical layer, because all of the porosity and permeability change every petrophysical layer. And so, again, the dark and the light just easily show you where all your petrophysical layer changes are. All right, so we'll leave that at that. I'm going to go ahead and put a suffix here. I mean, if we just run one sim, we don't need it, but I'll just call it region 1. You put whatever, if you're going to be running multiple ones, it's just handy to put in something that designates what's different about this particular sim. In this case, we're running OBM2. Maybe the next one we'd run OBM1. You normally should not have to deal with the numeric configurations, but there are special cases where you could, if you're having problems getting the thing to run, you may want to shorten these with the understanding that it might not be as accurate. And then you have some no flow criteria here. Just keeps it from getting to keeps it running smoother usually, because if you get, whenever you get certain parameters near a limit, it will sometimes get a little unstable. So then up here you have these buttons that are sort of shortcut buttons, some of them, so for instance we have the rock button, and that takes you to the table where it shows you the parameters relevant to fluid flow that you can change in each layer. So the porosity, permeability, shale concentration, and so forth. And then similar thing for fluids, you'll get the fluid, it'll just show you the fluid properties that you can change. PCKR curves. I don't think we're actually changing any of these, but this is where you could change these. And so these go by basically every rock class has one. And so if we want to add a new rock class, we might have to, class 1. So each rock class so if we had class 1, we could change these parameters, for instance, in class 1, and then you can see that you can go back and forth and see the values for each rock class. And so typically by default, we have these set of models that you can use. So there's a PC models, Brooks Corey, Van Gnuchten, Tamir, Lehorn, modified Brooks Corey. And then you also have data. And if you choose data, you'll see this changes from a smooth curve to dots. And those dots represent in this case, the PC values that you see in this table here, and those you can change manually. If you have it set to data, I could make this one be 1.7 instead. And you see that this first point here changed to 1.7. But instead, we're going to stick with the modified Brooks score here, default. And you have a similar thing over here for the KR models. You have the Purcell, Berdeen, Milam, and these change if you have a model selected in the capillary pressure. Then Purcell and Berdeen and Milam, they take on different forms based on the PC model, and so that's taken into account in here. And so if you want to see more information about it, you can click on this. And these show you some of the definitions that we have. And so then you can also you can see what you can look at different layers if you want to. Or you can just look at the reference rock class, and that really has to do with what your fluid values are and stuff. So basically, because the PC values will change based on the porosity and permeability in the layer. And so if you choose the reference one, it shows you those values relative to the reference permeability and porosity. But if you choose a particular layer, those values will change. And if you want to see all of them at once, then you can go to the next tab, and this allows you to see all the variation that you have in your in all your layers as far as the PC curves, or you can also view the KR curves if you want, both of them. And you can change the color of different ones. You can change them by class or by just individual layer if you want, just to see a particular layer. You can choose which ones you want to view. You just want to see the modeling interval or all depths. If you want to see the ones from the same, you can also set the rock class here. So we want to set, for instance, this one, we could make it rock class 1 if we wanted to. You see that because we had changed that rock class PC curve, we see it showing up very differently. And we can also see layers from the same rock class. Or a custom. We'll look at all of them. Oh, I think it's from the same rock class as the ones that you select. Let's see, change this back to default. Okay. So if you have your own, if you calculate your own curves, you can paste those in here as well from outside. And then if you have more than one well, you can switch wells too. In this case, we're going to be using the default, and let's see. Okay, so we set that, and so now we're going to run the, I guess I should have started the simulation while I explained all that other stuff. Okay, well, I still got a couple more tabs. So we're going to start this simulation. Oh, wait, actually, I'm going to end the simulation. because I wanted to run at 1D. It's going to be end up being a little bit faster. Actually, in this case, a lot faster. Okay, yeah. So we'll change this to 1D and then run this again. Okay, so while that's running, and you can see the runtime here, and it'll show that it's done when it's done. Some other things here, you can adjust your mud cake parameters if you want. You can either set them directly in here, or if you have static filtration test values, you can put those in here, and then it will calculate these values. I know Hamid Benes said that he actually got values from the service company for these filtration tests and used this to calculate the mud cake values, mud cake properties. And then in the advanced, we have trouble. Okay, wait. Need to move this down, I think. Advanced, there we go. You can set up at the top some properties for water if you want to change your water properties slightly, or some of the hydrocarbon properties. There's several different viscosities you can use. Later we may go into the other model which we have which is a single phase model. This one is a multi-phase model, and it'll take into account all the different oils that we have involved. And down below here, you have the option of closing the command window after the simulation. In this case, we have it unchecked, so this is going to stay open, so you can see if you want to review anything that occurred in the simulation or look at errors. You also have save partial sim data on abort. I don't know if you saw, but the when I canceled that 2D sim, it said it was saving the partial sim data. In that case, I didn't really want it to, but sometimes you'll run long sims and you'll want to save the data. So you might want to finish it early and save the data. And then the maximum number of times per decade. This sort of reduces the amount of data that you end up saving in your project, because sometimes if there's difficult Earth models, there can be some the sim can sort of get stuck or slow down a great deal at different time steps. And so you could end up with 100 or 1,000 sim steps, and you don't want to save all of those. And so what this does is it just, in the end, when it processes the data, it just says, okay, I'm just going to save 40 of those steps. Because you don't need 1,000 steps in 1 decade of time. And then under fluids, you have a choice between oil and water, or gas, oil, water, or gas, water. In this case, we're just using oil, water, because we just have the 2-phase. And the oil-water contact is maybe something that we'll show later, but if you don't have don't have your own calculation of the water saturation and pressure, what this allows you to do is to designate a depth for the oil-water contact. Everything below that will be 100% water. And then and you set a pressure value there, and then based on the capillary curves for all of the layers above, it will calculate what the water saturation should be. And so that's one way of getting a more complex, especially if you just have a, you know, say a single large layer, but you want to get finely tune the water saturation throughout that layer, you can use this. And then down here, we have well, actually it gives a little description of it, but you have three different initializations. One is a petrolayer average, one is full earth model fluids, and the other is formation fluids. So by default, we use formation fluids because that just takes the farthest out formation layer values that you have and use that to populate the initial fluid population that it will invade. But if you want to, for instance, say you run an invasion and then you want to do another invasion, or you want to do a formation test on that invaded fluid, you can select use full earth model values, and then it will interpolate the values in the earth model for all the fluids and all the zones into whatever your fluid flow grid is, and then you'll invade into that or test out of that. All right, so this finished about 5 minutes. And so one of the things that you can do here is import the results. Or I mean, we're going to import the results, but you can also plot the results beforehand to see what you have. So if we want to see like the total water saturation, or I don't think our salt concentration will change, but let's just look at the total water saturation. I guess we can look at the oil too. So you can look at history, distribution, or vertical cross section. And we wanted to do 0.025, but we went out to 0.5. So if we want to see what the difference will be, in here we can select 0.025, and we can plot 2 times. So now we'll get 8 plots. So we can set this to put 8 plots on one sheet. If you don't put 8 plots on one sheet, it'll take as many sheets as it needs based on the layout that you give it. And then we can plot it. And this is like a preview where you can look at different simulations that you ran without having to import them into the Earth model. So you can just see what the results were. And so in this case, we can see the over that time, the water saturation history, as it dropped down a little bit, and the oil saturation went up by a similar amount. And note that this is at, we just picked one radius, so this is at the borehole. And then you can also see the radial distribution, and this is sometimes useful to see that that you're not hitting the limit in your simulation by having. So out here you should have no change near the outer radial limit, and then down here you can see the 2D distributions, radial distributions, well, radial and vertical distributions as a function of the day. So you can see, you know, how much more invaded this was at 0.02 days versus 0.05 days, for instance. And oddly enough, it looks kind of strange, but total water saturation kind of looks like it didn't change. Well, there's some invasion up here. I'm just not sure here. Okay, so depth is 1.160. Look at all the depths. 0.05, 0.025. Well, I think we had everything set up right, 0.05 days. All right, well, let's try to import that. Somehow that actually looked a little different than I expected, but let's see what we get when we import it. Okay, so in this case, I'm not going to recalculate after importing. I'm just going to import this. Oh, and I'm importing 5 days. So actually wanted to import. So what I wanted to show before was that since we wanted to import 2.5, you can actually simulate 5, and then you can look at different values and pick what and import at whatever time that you want. So instead, I'm going to do this one, and then I'm going to get this. So now we can see that we have different invasion profiles based on you can see, so actually I need to show the, I'm going to put the OBM up here. Okay, so in here you can see we have the water and then our 2 original oils, and then you see in the dark is the invaded. And so as we move in our first invaded zone, we have pretty much 100% invasion just about. But then as we move out, you can see that it becomes less and less until we finally get back to our original oil. So so the purpose of this is to see what effect these different invasion zones will have on our, or this OBM invasion will have on our NMR. And so in order to do that, first we have to, similar as always, we have to calculate. Now the applied DOI is going to be really important because we have 50 zones there, and we only want to calculate out to, less than a foot. And so we'll keep the settings that we had. We just changed the oil. And so now you can see, whereas before it only calculated zone 2, now you see here that every layer it's calculating out to zone 11 or 12. And so the key is that we wanted to try to get a try to pick a depth of invasion that's going to give us some mix of oils in here. And so we'll have to see how good of a job we did on that. All right, so we now have the new, so now in here, now we are going to give this a different name. We're going to call it NMR simulation invaded. We'll leave everything else the same, and we'll simulate this. And then really deep. One thing that many people suggest that I put a box here that says when this is done. It is really fast, but it does take a couple of seconds. So anyway, then if we go here, actually, since I'm able to check it because I'm here, so it's finished because I'm using the MB version. So now we want to invert this. So now we be sure and change to the inverted sim. And we're using the same sequence. And now another difference is now we do have invasion. So we want to invert all zones. The simulation by default, or well, the simulation actually not even by default. It just, you don't have any choice. It will simulate the 3 different shells. But in the inversion, you don't have to invert for all the shells if you don't want to. But we will in this case because we want to look at what the different ones look like. And then stack, again, for the time being, we'll leave it at stack 1. So basically the rest of this, we're going to leave at what we had before, and we just want to see the difference between having the mud. So we'll go ahead and invert. And if we want, we can check the inversion analysis. It looks pretty good, actually. A little bit off, but and then okay. And so now, if we want, we can maybe make these a little bit smaller and make room for another distribution. Now, there's actually 2 things that we can look at. I'm having a hard time grabbing that. Okay, so I'm going to insert 2 tracks. The first one, I just want to look at a vertical cross section. I want to see if we can see what our invasion looks like. So we're only interested in about really a foot, but let's make it 0.5 meters. Maybe I'll make it 1 meter. And then what we want to see is where that invaded oil comes. I think we have a fluid. Oh, maybe we don't have a fluid. Joaquin, don't we have a fluid composition?
I think maybe not in this version.
Okay. Okay, well, I guess I thought maybe we could pick the
no,
particular...
but you can do it, but it's not in the vertical cross section. It's in the composition.
Oh yeah, it's in the composition. I wanted to see a vertical. Let's see, maybe no, the water resistivity isn't really going to show it. Or the water saturation isn't really going to show it. I mean, it shows a little bit, but yeah, I wanted to see to actually see the oh, maybe actually, you know what, maybe maybe I can see that in the viewer. I might have picked the wrong plot. Maybe I need to pick this. And that's what I was looking for. Okay. So in this case, I was able to plot the 2D, just show you the actual the OBM fluid. And this shows how our invasion looks of the OBM into the formation. So you can see where it was invaded. That was the one I was trying to find before. I was looking at total oil and saturation. Those get all mixed up because they don't really show you what you want to see for the invasion. But this does. This is what I was looking for. So you can plot different. Again, you can plot the radial distribution at different points if you want, or just look at it like this. But so here you can clearly see the invasion. Okay, so I guess I could have left that open too. If I wanted to see, so this is about 10 inches.
Excuse me, how can the invasion can be so far in the shell as per the simulation result? I see that both above shell and bottom shell have higher invasion.
Well, it's because they're not pure shale. And so the sand, we still allow the invasion in, and so it's really showing the it's really just showing the fraction that goes into the sand portion of that layer. And so and I mean exactly why it comes out to be more. I mean, like up here, you can see. I forget what time this is. Okay, so that's invaded 10. Now we can try invaded 8. So yeah, I mean, we seem to get like similar amounts of invasion. I think it has to do with like the amount of fluid that comes in versus the space that's allowed for it, and it just has to go in further to take in the same amount of fluid. That's my understanding anyway. But so now, yeah, so this one actually isn't worth plotting because we don't care that much about the water saturation changes. You can see there is a little bit of water saturation variation as well. But I think instead I'm just going to plot over this and make this into an NMR distribution. And in this case, we're going to pick the invaded, and we can actually choose different ones. Let's set it to be the right size. So I want 4 from 0.3. And so you can see we get a little bit of variation here, and we can look at the different the changes between that's 2.5. If we want, we can actually plot another one. put 4. So now you can see the effect between, or the difference between like the 2.5-inch shell and the 4-inch shell. And you can kind of decide which one you think looks better for the, probably the 4-inch one. Looks a little bit more like the one that we have here. And let's see, I think we also suggested yeah, we looked at some of the different zone profiles. I'm just checking to see what I had, what suggestions I had to in this particular version to do after this. Okay, so we're looking at the different shells. So one of the things, I guess the other thing that we suggest is that it might look like the some of if these are water peaks, maybe some of them should be moved a little bit higher. It looks like these are kind of low, whereas here the peaks are a little bit higher. So we could try moving the matrix. The rock class. So you could try increasing the pore size of the rock class slightly. So in here I say by 10, which seems like a lot, but we're starting at 1. Let's just make it by 5. Let's see what that does. And so this is just one of the many things you can play around with. You can also put multiple peaks in there if you wanted to. And actually we could try that since we're kind of playing around. I'll show you how to do that. So you can just add another peak, and we can have the one at 5. And then if we want, we can put the other one back down here where it was at 0.1 or 0.2. I forget where it was. 0.1, I think. That might be too much of a distribution. So here you can see we have a bimodal distribution. And if you want to see what effect that would have on the, oops, that's in class 1 though. It's actually a default class that we want to change. So here we'll add one. And we'll put it up at around 5. Let's make it exactly 5. Oh, I had less. Okay. Yeah, if we want to see what effect that will have, then we can just run this thing again. And after a while, the sequence, you just get used to the sequence that you just run over and over again. Oh, and I forgot, well, the other thing, we can also, on the new one, make another T2 T2 mean log plot to put on top of it. I'll run this one, or I'll run this update first and see what how that does. But one of the things that we were after here was to try to see, not just to move the peaks, but to try to see a little bit more variation, which I think we do here than we did over here. So it looks a little, in some ways, it looks a little bit more like the original imported value. Okay, so let me do the simulation. So overwrite it. And then make sure that it's done. Okay. And then inversion. And then we'll plot these and we'll say that that's close enough. I mean, there's other things that you can try, like play with the stacking and stuff, because we didn't really know what stacking we had in the imported data. And now let's see. Do 2.5. Okay, so pick the correct one. Okay, so yeah, so you can see here. Actually, I'll replot both of them. Yeah. So you can see here the effect that we had with adding that, adding an additional higher peak. It sort of makes it look a little bit more like the original one by moving these peaks in the oil zone up a little bit, and also adding some variation to them. So that could be a possibility. And then the final thing we can do is just add for completion, add the T2L log set. And I'm just going to get this to look like the other one. Okay, so anyway, yeah, but this kind of shows you the effect that you can have with the invasion and the NMR Studio mixed together. And I think it's especially important with the NMR Studio because it handles near borehole effects, and so it really makes a big difference on the NMR results, as we can see here, even just between the 2.5 inches and 4 inches. But this, I think, looks a little bit more like this, but you can continue to play with this sort of thing and probably try to get it closer and work on the individual layers and stuff. But I just wanted to give you an idea of the types of changes that you can make that will make your simulation look more like the imported